Welcome to the Deep Dive. Today we're diving into a collection of research papers about material science. I mean, we've got a pretty diverse mix, right? From microwave absorbing materials to stuff about making rocket fuel. It's really interesting.
Yeah, it is. And it's really fascinating how these seemingly different areas, they all connect. It sort of highlights how innovation, can have a ripple effect across all these fields. Aerospace, electronics, even energy.
Okay, let's start with something that sounds kind of like right out of the science. This first paper, 2001.0226261.pdf, it's all about a material that can absorb microwaves.
Yeah, it's ingenious actually. They created this thing, it's called a castable microwave absorber. They use a blend of magnetite powder and a special type of plastic. You can think of it like a high-tech recipe.
Okay.
And you can adjust the ingredients to control which microwave frequencies you absorb.
Oh, so by tweaking the recipe, they can target specific frequencies with the advantage.
Well, that's the key, right? They created a tunable absorber. And that kind of control is crucial for tons of applications, like scientific experiments, where you need to get rid of certain frequencies to get really precise readings.
Okay, so it's like making a filter for microwaves. It reminds me of those anechoic chambers. So quiet, they absorb all the sound waves.
Exactly, similar concept. Those chambers stop reflections of sound, and this material, while the name is the same with microwaves, has big implications for radar technology. Potentially.
Oh, that is interesting. They even mentioned in this paper about using this model to understand how this material interacts with microwaves and different frequencies. It seems pretty high-tech for something that uses what sounds like everyday materials.
Yeah, that is pretty remarkable. It just goes to show that innovation doesn't always require some exotic new material. Sometimes it's just about using what we already have in a clever way. And, they give all this detailed information about their process too. For example, they use this tool called a vector network analyzer to measure the material's properties. And to get this, up to 170 gigahertz.
170 gigahertz. Wow. Okay, so what would you say is the big takeaway from this paper for someone like me who thinks this is fascinating but isn't a scientist?
Well, think about it this way. This research could lead to smaller electronics that are also more powerful, more efficient wireless networks, even more accurate medical imaging, all because of a material that can absorb microwaves.
Yeah, that's wild. Okay, this next paper, 2011.07872v1.pdf, it's all about this material called barium titanate. Can you just give us a quick rundown of what makes that material so special?
Sure. So barium titanate is a ceramic.
What?
And it has some really remarkable electrical properties. You find it in capacitors, which are those essential components in, everything really. Yeah. Smartphones, laptops, even those advanced power systems.
Okay, so it's already used in tons of the tech we use every day. What are these researchers doing that's new?
Well, they're doping it. That means they're adding these tiny, tiny amounts of other elements like gallium and tantalum to really fine-tune how it performs. You see, even those super small changes at the atomic level can drastically change a material's properties. And in this case, they were able to adjust the temperature range where it works best, how it responds to electric fields, and they even found a way to reduce energy loss.
So it's like they're master chefs.
Right.
Adding a pinch of this and a dash of that to perfect the recipe.
Yeah, exactly. That's a great analogy. And that's important, right? Because it means you can create these custom versions of barium titanate for different applications.
Oh, so to improve the efficiency of a capacitor in my smartphone, they could use a specifically doped version of barium titanate. That's cool. This paper is really detailed too. It talks about the ratios they use, the techniques, things like ball milling and isostatic pressing, which I have to admit I'm not really familiar with.
Right. They've been really meticulous in outlining their methods. And they've also gone deep into analyzing the structure and properties of the material. So they use XRD analysis, the technique, to confirm that they were creating the right crystal structure. And then they really carefully measure things like density and the lattice parameters, all very precise,
Yeah, very detail-oriented work for sure. Okay, so this next paper, a study in technology development, performance, and .pdf, it takes a step back from the lab and looks at, the bigger picture of how technology gets developed, right? Specifically, it focuses on small and medium enterprises, SMEs, and what helps them succeed when they try to bring new technologies to the market.
It is a good reminder. Having great ideas is just the beginning. To turn them into products you can actually use, you need investment, expertise, and the right kind of environment, right? To really foster that innovation.
Okay, so it's not just about that eureka moment. It's about the infrastructure to support it. What did they find were the key ingredients for these SMEs?
Well, they looked at data from a survey of Korean SMEs, and they found that investing in research and development, having a skilled workforce, and access to specialized research centers, all of those were really important, both for technological success and for commercial success, And what's interesting is that they looked at how those factors played out differently across a variety of sectors, from high-tech to low-tech industries.
Interesting. So you're saying that there's no one-size-fits-all approach when it comes to innovation.
Exactly. It just highlights how complex that innovation ecosystem really is. It's not just about scientific breakthroughs. It's about creating those conditions where those breakthroughs can really flourish.
Right. All right. I am ready to get back to some cutting-edge materials. This next paper, Carbon-Based Radar Absorbing Materials Towards STI.pdf, caught my eye because it's about stealth technology. Come on, who hasn't dreamed of having an invisibility cloak, right?
Well, stealth technology is definitely captivating, and this paper goes into using carbon-based materials to make these radar-absorbing materials, or RAMs. Yeah. They work by, well, they minimize those reflections of radar signals, and that makes objects harder to detect. Carbon-based materials are really good for this because they're lightweight, highly conductive, and can handle some pretty rough conditions.
So no invisibility cloaks just yet, but we're getting closer to making things much harder to find on radar. What kind of carbon are we talking about here?
Oh, they explore a whole bunch of different types being used in rams. Everything from carbon black, which is pretty cheap and easy to get, to more advanced stuff like carbon nanotubes, graphite, graphene, even something called MNASI, and they each have their own unique properties and advantages.
Wow, like they're building a toolbox for stealth technology. It's amazing, and I go into so much detail in this paper about all the different ways these materials can absorb radar waves. I'm learning a whole new vocabulary.
Right.
Like dielectric loss, magnetic loss, dipole interfacial polarization. It's fascinating.
Yeah, and understanding those mechanisms, that's key to designing these effective rams, right? You need to know how that material is interacting with the electromagnetic waves at that atomic level to get the best performance.
Wow, there's some serious science going on behind all this. Okay, so last paper for this part of our deep dive is REMA Game Changer Rocket Propellants 2021.pdf. And we're switching gears from stealth to space, or at least rocket science. This one focuses on something called resonant acoustic mixing. That's RAM too, and how it's impacting how we make solid rocket propellant.
It's a great example of how a technology, seems completely unrelated, but it can be used to solve a problem in a totally different field. In this case, it's not about radar absorption. This RAM, it's a mixing technique that uses sound waves to blend the ingredients for solid rocket propellants.
Using sound waves to mix rocket fuel. That's wild. Can you explain how that works? Why is this new mixing method such a big deal for rocket fuel?
Well, you see, traditional mixing methods, they don't always work well with those really thick, viscous materials. And you get a lot of that in those propellants with a high solid content.
So what does high solid content even mean when we're talking about rocket fuel?
Oh, sorry. Basically, it means they're packing more fuel into the propellant. And more fuel means more powerful rockets, right?
Nice.
So this RAM, it's great at mixing those viscous materials. It makes a more homogeneous mixture, if that makes sense, more consistent.
So using sound waves makes a better, more powerful propellant. Are there any other benefits?
Oh, yeah. It's not just better mixing. RAM can improve the performance and the burn rate of propellants, making them more efficient. And maybe most importantly, it makes things safer during manufacturing. Those conventional mixing methods, they can generate a lot of heat, which can be a problem when you're working with materials that, could explode. But RAM, it operates at lower temperatures, so it's less risky.
Oh, okay. That makes a lot of sense. Safer and more efficient rocket fuel. It's like fine-tuning the rocket's power source, really.
Yeah, that's a good way to put it. They're focusing on a type of propellant called HTPB-based propellant. It's really common in solid rocket motors. And they're looking at how RAM can help with those challenges of mixing it at those high solid loadings and even, figuring out how to add nanoparticles.
Wait, nanoparticles in rocket fuel? What? Is that even possible?
Oh yeah, it sounds futuristic, I know, but it's real. Nanoparticles, they can actually improve the burn rate and efficiency of that propellant, which gives you an even more powerful and controlled burn.
Nanoparticles are really changing everything these days. I have to ask, the paper also mentioned in situ RAM. What is that all about?
That's a really fascinating concept. It means they mix the propellant right inside the rocket rotor. You don't need a separate casting process. It's kind of like 3D printing for rocket fuel in a way.
Oh, wow. So they're streamlining the whole manufacturing process. That's amazing. This in situ RAM, it seems like it could really revolutionize how we build and handle these rocket propellants and make everything safer and more efficient. It's just incredible to think about, This technology, it started as a way to mix things, and now we're talking about making better, safer rocket fuel. Pretty incredible stuff.
It really speaks to, how clever these engineers and scientists are, always finding new and creative ways to take existing technologies and use them to solve new problems.
Well, I think we've covered a lot of ground in this first part of our deep dive. From microwave absorbers to rocket fuel, we've seen how material science is pushing the boundaries of what's possible.
And we've only just scratched the surface.
Exactly. But before we jump into the next batch of papers, let's take a quick break.
Sounds good. Welcome back to the deep dive. I'm still thinking about all those advancements we talked about. It's just amazing, how those tiny changes to what a material's made of can have such a huge impact.
Yeah, it's pretty mind-blowing. From, materials that can make things practically invisible to radar to the stuff that powers rockets. It's clear that material science is, shaping the future. And, before we get to the next paper, I want to go back to something you said about resonant acoustic mixing. RAM, for those rocket propellants.
Yeah.
You were talking about how it's really important to understand exactly how those sound waves are interacting with the materials to get a good mix.
Right. It's not just about hitting the ingredients with sound. It's a real science. You have to fine-tune everything. The frequency, how strong the waves are, even how long you apply them. It all depends on the materials and what you're trying to make.
So it's kind of like a conductor leading an orchestra.
Yeah.
You have to know how each instrument's going to contribute to the overall sound to create a masterpiece.
Yeah.
So how do scientists know if the mixing is actually working? I mean, how do they test the final product to make sure it's good?
That's a good question. It's like being a detective almost, gathering clues, They use all sorts of techniques, like microscopy, where they can actually see how the particles are spread out in the mix, and spectroscopy to check what chemicals are in there. And then there's rheology, which measures things like how thick it is, viscosity, and how well it flows.
So they're really looking at it from every angle to be sure that it meets the standards, right?
Mm.
For something like rocket fuel. It's fascinating how much precision goes into it.